Standing across the Yenisei River, Sayano-Shushenskaya is a mega dam that has become an energy symbol of Siberia. When completed, the plant reached a capacity of up to 16,400 megawatts, making it the largest hydroelectric power plant in Russia. To build this project, the Soviet Union had to spend decades constructing it amid snow, ice, rocky mountains, and a massive river that was never easy to conquer. But what made Sayano-Shushenskaya famous was not only its scale. Behind its 242-meter-high concrete wall is the story of one of the Soviet Union's most ambitious engineering projects, along with one of the most serious hydroelectric accidents of the 21st century, which forced the entire global hydropower industry to rethink its safety standards. Join Mandarin Tech as we explore the story behind this mega dam in the heart of Siberia. At the height of the Cold War, the Soviet Union did not compete with the West only through missiles or nuclear submarines. That competition also took place inside metallurgical plants, mineral mines, and massive industrial complexes stretching across Siberia, where electricity consumption was so enormous that only mega hydropower projects could meet the demand. For Soviet planners, the Yenisei River was seen as an almost endless source of energy, flowing wastefully into the Arctic Ocean every day. If they could harness the power of this river, the Soviet Union would have access to cheap electricity, strong enough to operate strategic industrial zones for decades. It was from that ambition Sayano-Shushenskaya was born. For many years, this power plant served as the energy heart of Siberia, providing a massive supply of electricity for the entire region. However, after decades of operation, a horrifying incident occurred. In 2009, Unit 2 was suddenly destroyed after the bolts holding the turbine cover in place broke, taking the lives of 75 people and becoming one of the worst hydroelectric accidents of the 21st century. Yet even in the middle of that disaster, the dam body remained standing, preventing a scenario that could have been far worse. The story began in 1963, when the Sayano-Shushenskaya project officially started construction. But before the dam could be built, Soviet engineers had to do something that seemed almost impossible: divert the Yenisei River away from the construction site. This was not an easy task. The Yenisei is one of the largest rivers in the world, with an enormous volume of water flowing through the canyon every day. Meanwhile, the construction site was located in Siberia, where winter temperatures often drop below -30 degrees Celsius. The ground and rock remained frozen for many months. The annual construction window was significantly shortened, and operating heavy machinery became far more complicated than on ordinary construction sites. To solve this problem, the engineers chose a river diversion method using a system of tunnels through the mountains. First, construction teams drilled and blasted the rock on both sides of the canyon to create diversion tunnels capable of carrying the full flow of the river throughout the dam's construction period. After the tunnels were completed, the project moved into the stage of building upstream and downstream cofferdams. Millions of cubic meters of earth and rock were transported to the site and continuously dumped into the riverbed to gradually narrow the main flow. When the cofferdams reached their designed elevation, the river water began to be fully directed into the diversion tunnel system. The section of the riverbed inside the cofferdam area was then pumped dry, and the layers of silt, sediment, and accumulated alluvial material that had built up over thousands of years were removed. This was also the moment when the Yenisei River had been completely diverted. After the river had been successfully diverted, the construction site had to carry out a large-scale foundation treatment campaign. Construction teams used drilling and blasting to remove the weathered rock layer and unstable soil and rock above the bedrock. More than 10 million cubic meters of material were excavated, exposing the stronger rock masses underneath. After the foundation excavation was completed, the engineers began a detailed survey of the bedrock surface. Natural cracks were identified, cleaned, and treated using high-pressure grouting. Thousands of boreholes were drilled to pump cement grout deep into the rock foundation, helping reduce water seepage and increase the stability of the entire dam foundation area. At the same time as the foundation reinforcement process, inspection galleries and technical tunnels inside the bedrock were also constructed. These structures allowed engineers to access the foundation area during later operation, while also monitoring water seepage, deformation, and stress developing beneath the structure. Only after all foundation treatment work had been completed did the construction of the dam body truly begin. Sayano-Shushenskaya was designed as an arch-gravity dam, a massive structure that combines the weight of the dam body itself with the curved shape of the structure to transfer water pressure to the rocky mountain slopes on both sides. To build this project, Soviet engineers did not construct the entire dam all at once. Instead, they divided the dam body into many separate blocks, then poured concrete layer by layer and stage by stage. However, the biggest challenge did not come only from the enormous volume of concrete, but also from the harsh climate conditions of Siberia. The summer was short, but temperatures could change sharply between day and night, while the winter lasted a long time with extreme cold. At the same time, the hydration process of cement continuously generated heat inside the concrete mass. If the temperature was not tightly controlled, the difference between the core and the surface could create dangerous cracks. To solve this problem, the concrete temperature was continuously monitored by a system of sensors, while the concrete pouring schedule was carefully calculated to limit thermal stress. At the same time, a large-scale material transportation network operated almost non-stop to supply concrete to the construction site. Layer by layer, the concrete gradually stacked up. 50 meters, 100 meters, 150 meters, and then even higher. In the middle of the western Sayan Canyon, a giant wall began to take shape. The higher Sayano-Shushenskaya rose, the more it had to face another life-or-death challenge. Behind this dam is a reservoir with a capacity of more than 31 billion cubic meters of water. Under normal conditions, it is a massive source of energy that powers Siberia's industrial zones. But during flood season, that same body of water, weighing tens of billions of tons, can become a threat to the structure. If the flood discharge capacity is not sufficient, the water level behind the dam will continue to rise and create pressure beyond the design limits. That is why Soviet engineers had to build one of the most important spillway systems of the entire project. The work began with large-scale drilling and blasting operations to create a construction platform in the middle of rugged, rocky mountain terrain. After that, concrete was poured continuously to form water channels, guide walls, and energy dissipation basins, structures whose purpose was to control and reduce the force of the water before it returned downstream. When the structural work was completed, large steel gates and mechanical control systems were installed to regulate the discharge flow under different operating conditions. At the same time, engineers continuously used hydraulic models and flow calculations to test the flood discharge capacity of the entire system. However, no matter how massive a dam is, it is only a place to store energy. To turn the enormous body of water behind the dam into electricity for Siberia's industrial zones, Soviet engineers also had to build the true heart of the entire project, the Sayano-Shushenskaya hydroelectric power plant. Right below the foot of the dam, a massive volume of rock was excavated to create space for the turbine hall, the generator hall, and a series of auxiliary technical structures. After the foundation was reinforced, concrete was poured continuously to form the framework of the power plant. This was not just an ordinary civil structure, but a facility that would have to withstand the force of a water column hundreds of meters high, along with the weight of the enormous electromechanical equipment inside. At the same time as the power plant was being built, large pressure pipes and the water intake system were also constructed. These structures acted like arteries, carrying water from the reservoir down to the turbines. During operation, the potential energy of the massive body of water behind the dam would be converted into kinetic energy as it rushed through the pressure pipes, spinning the giant turbines directly connected to the generators. After transferring most of its energy to the generating units, the water continued to be discharged back into the Yenisei River through the downstream outlet channel system. However, even after the dam body and the hydroelectric power plant had been completed, Sayano-Shushenskaya still could not generate electricity. To harness the power of the Yenisei River, Soviet engineers still had to install the largest hydroelectric generating units ever built in the country. These machines could not be transported as a single piece. The turbines, shafts, rotors, and stators had to be manufactured at factories and then transported to the construction site as many separate components. Inside the machine hall, heavy-duty overhead cranes continuously lifted and lowered parts weighing tens to hundreds of tons into their exact designed positions. The rotor of each generator alone weighed about 920 tons, while the entire generating unit was a massive electromechanical system designed to operate continuously for decades. The greatest difficulty was not in bringing these machines into the power plant, but in the precision required during assembly. During operation, the turbine would rotate at about 143 revolutions per minute under the force of a water column hundreds of meters high. With equipment of such enormous size and weight, even a small error in alignment could create major vibrations, reduce efficiency, or cause serious damage to the entire generating unit. Therefore, each piece of equipment had to go through months of alignment, concentricity checks, vibration checks, and mechanical testing before it was allowed to operate. After the entire installation and test running process was completed, the generating units were gradually connected to the national power grid. In the end, Sayano-Shushenskaya was equipped with 10 generating units with a total capacity of up to 6,400 megawatts, becoming one of the most powerful energy projects ever built in the world. For decades, water from the reservoir continuously flowed through the giant turbines, providing electricity for metallurgical, mining, and heavy industrial complexes across Siberia. However, on August 17, 2009, a disaster occurred right inside the turbine hall of the power plant. After many years of abnormal vibration, the anchor bolts holding the turbine cover of Unit 2 broke. In just a few seconds, the enormous water pressure blew the entire upper structure apart, threw the generator rotor weighing about 920 tons out of place, and caused water to violently flood into the machine hall. The disaster took the lives of 75 people, becoming one of the most serious accidents in the history of modern hydropower. However, what is worth noting is that the cause did not lie in the dam itself. While the power plant was heavily devastated, the Sayano-Shushenskaya dam body remained standing and continued to safely hold back the enormous reservoir behind it. After the accident, Russia launched one of the largest hydroelectric power plant restoration programs in the country's history. Thousands of tons of damaged equipment were removed from the machine hall. The old generating units were gradually replaced with a completely new generation of turbines and generators. At the same time, the control, monitoring, and operational protection systems were redesigned with safety standards far stricter than before. A series of sensors monitoring vibration, temperature, pressure, and the operating condition of the generating units were installed to detect early signs of abnormality. The restoration process was carried out in stages, both to maintain electricity supply for the Siberian power grid and to gradually bring the plant back to full operation. By 2014, the final generating unit was officially connected to the grid, closing the journey of revival for this hydroelectric project. Behind the 242-meter-high concrete wall is another massive structure that many people often overlook, the Sayano-Shushenskaya Reservoir. When the filling process was completed, water from the Yenisei River gradually rose between the western Sayano Mountains, forming a reservoir more than 300 kilometers long with a capacity of about 31 billion cubic meters of water. The reservoir was so large that it completely changed the terrain of the entire area. Many former river valleys, floodplains, and low-lying areas disappeared beneath the water, making way for one of the largest artificial lakes in Russia. From the air, the reservoir stretches out like a vast inland sea winding between the mountains of Siberia. For the Sayano-Shushenskaya system, this reservoir acts as a huge storehouse of energy. Thanks to the water stored behind the dam, the power plant can maintain stable electricity production even when the flow of the Yenisei River changes sharply with the seasons. The role of the reservoir also goes far beyond electricity generation. In spring, when melting snow in the upstream mountains causes the water flow to rise sharply, the reservoir helps retain part of the floodwater before releasing it downstream in a controlled way. In contrast, during periods when the river flow decreases, this stored water continues to be used to maintain power generation and stabilize the flow of the Yenisei River. Today, Sayano-Shushenskaya does not simply provide electricity for Siberia. This project is one of the foundations that helps Russia maintain its position in the global aluminum industry. Aluminum is a strategic material widely used in aviation, defense, transportation, and many other modern industries. Producing 1 ton of aluminum requires about 13,000 to 15,000 kilowatt-hours of electricity. Electricity costs often make up a large part of production costs, so access to stable and low-cost hydropower becomes an extremely important competitive advantage. It is the electricity from the hydropower system on the Yenisei River, with Sayano-Shushenskaya at its core, that has helped sustain the operation of Siberia's largest aluminum smelting complexes for decades. As Russia seeks to maintain energy security and reduce dependence on fossil fuels in some regions, Sayano-Shushenskaya continues to play the role of a strategic national asset. More than 50 years after it was built, this project is no longer simply a dam or a power plant. It has become an important link in the modern Russian economy. Sayano-Shushenskaya shows something interesting about megaprojects. The hardest part is not building them, but keeping them operating across many generations. From an industrial ambition of the Soviet era, this project has survived a harsh climate, enormous engineering challenges, and even a serious disaster to continue existing today. Perhaps that is the true measure of a great structure, not how massive it is when completed, but how much value it can still create many decades later. If you found this video interesting, don't forget to hit like, subscribe to the channel, and follow Mandarin Tech to discover more engineering marvels around the world.